In this module, we are going to talk about linear programming. In particular, we will focus on how to formulate the linear programming problem and how to use graphical illustration to help us solve two decision variable linear programming problems. So let's start with the simplest example that has only one decision variable x. Let x be real numbers. What is the maximum values of x and what is the minimum value of x? Without any constraints, we know that x could range from minus infinity to infinity. Now, suppose we have the constraint such that x is at least 28 and at most 75. Then what is the maximum possible value of x and what is the minimum possible value of x? It is straightforward that the maximum is 75 and the minimum is 28. In this example, we are trying to find a maximum or a minimum value within the constraints, and this is what a linear programming model wants to achieve. Next, let's try a two decision variable example. There are two decision variables x and y. Let's say we want to find a value for x and y such that we can maximize the quantity of x plus y. However, we are faced with the constraint such that x must be between 0 and 3 and y must be between 0 and 5. From the graph, we know that any x and y combinations that lies in the pink shaded area is a feasible solution for x plus y, but it is not clear from the first glance that which x and y combination will give us the largest x plus y value. Let's do some trials. Let's start with the x and y combination that will result in x plus y equal to 3. If we draw a line that represents x plus y equal to 3, then we find that there are feasible x and y combinations like above this blue line. This means that there are feasible x and y combinations that will give us a larger x plus y value. So how about x plus y equal to 4? Then we see again that there are still feasible solutions that will give us a higher x plus y value. How about x plus y equal to 5? We can still see that we still have other x and y combinations that will allow us to get a larger value of x plus y. At this point, you may have already observed that these three blue lines are parallel with the same slope. Because we want to find the maximum value of x plus y, we can move these lines parallel upward to find a better value of x plus y within the feasible region. Let's look at an animation to illustrate how this works. We see that the pink region is the feasible region for the solution. Let's draw a blue line that represents x plus y and say x plus y equal to 1. Then we move the line upwards without changing the slope until we touch the last point of the feasible region. And we can see that the best solution possible is at the intersection of the two lines x equal to 3 and y equal to 5. Therefore, 3 and 5 is the optimal solution, and the maximum value of x plus y equal to 3 plus 5, which is 8. In this same example, if our goal is to find the minimum value of x plus y, then we will move the blue line downwards without changing the slope, and the minimum of x plus y will occur at 0 and 0. So what is linear programming? In short, linear programming is a mathematical technique for maximizing or minimizing a linear function of several variables subject to linear constraints. Why do we want to use linear programming models? It is because many business problems require the decision maker to optimally utilize resources to achieve the goal. The goal, or what we call objective, could be maximizing the profit or minimizing the cost. And the limited amount of resources will be the constraint for the decision problem. How are we going to formulate a linear programming problem? Every optimization problem contains three components. The first component is the decision variable. Decision variables are the quantities that can be selected by the decision maker. These quantities are usually unknown before you solve the problem. The second component is what we call objective function. This is the goal of the decision problem. You want to choose the values of the decision variables to optimize the value of the objective function. The third component of an optimization problem is the constraint. Constraints are the limitations in the resources in pursuing the objective. Before we look at the example, I want to point out two terms. There are two types of solutions to an optimization problem. A feasible solution is a solution that satisfies all constraints, but it is not necessarily the best solution. An optimal solution is referred to as the best feasible solution. An optimal solution will result in the largest possible objective function value in a maximization problem and result in the smallest possible value in a minimization problem. Now we are ready to see an example. Suppose we have two decision variables x and y. Our objective is to maximize the value of 2x plus 3y. Therefore, our objective function is max 2x plus 3y. This maximization problem is subject to four constraints in the slide. We start by drawing the boundaries of these constraints. We first draw x equal to 3, and we know that the points that are on the line or right to the line satisfy the first constraint. Similarly, we draw y equal to 4, and we know that the points on the line or under the line satisfy the second constraint. We also need to draw the lines for the third and the fourth constraints. After we draw the boundaries for all four constraints, we check the feasible region. A feasible region contains all points that satisfy all constraints simultaneously. Therefore, in this example, the pink area is the feasible region. Any x and y combination in this pink region is a feasible solution to this optimization problem. Next, we will find the best feasible solution that will produce the largest value of 2x plus 3y. We start by drawing a line that has the same slope as the objective function. And we can start with 2x plus 3y equal to 6. I start with this value because I can easily identify that 3 and 0 is a feasible solution, and 2 times 3 plus 0 equal to 6. You may start with other right-hand side value. Now, I see that I can improve the objective function value by moving the line upwards without changing the slope. That is, I draw parallel lines that will yield a higher objective function value. I will continue to do so until I reach the less feasible solution in the feasible region. In this example, we see that the optimal solution occurs at the intersection of the two constraint boundaries, y equal to 4 and x plus y equal to 8. Therefore, we can solve the two quantities together to get the optimal solution. Next, I want to point out some observations for the solution of a linear programming problem. First, if there is only one optimal solution, then the optimal solution occurs at the corner point. Second, sometimes it is possible for a linear programming problem to have multiple optimal solutions. You can see such example in this slide. All the points on the blue line and within the feasible region are optimal solutions that will all produce the same maximum objective function value of x plus y. Finally, I want to point out that if a problem's constraints are not set properly, sometimes we may get into a situation in which problem is unbounded. For example, if you take a look at the optimization problem in this slide, you will see that the feasible region is unbounded. As a result, we can continuously move the objective function line to the right and never run out of feasible solution and can get the higher value of x plus y. We said that this linear programming problem is unbounded. Now, we have all the basic terms and concepts, and we are ready to see the applications. First, recall that there are three components in an optimization problem: decision variables, objective function, and constraints. Let's start with the decision variables. Mary can decide the number of regular lemonades and the number of strawberry lemonades to sell each day. So, these two quantities are the decision variables. Use x to represent the number of regular lemonades, and we use y to represent the number of strawberry lemonades. Next, let's look at the objective function. Mary's objective is to maximize the profit by choosing the best quantities of regular and strawberry lemonades to sell. We know that Mary will sell x regular lemonades, and each regular lemonade's profit is $2. The profit from selling regular lemonades will be 2x. Similarly, Mary will sell white strawberry lemonades, and each strawberry lemonade's profit is $3. So the profit from selling strawberry lemonades will be 3y. Mary's total profit will be 2x plus 3y, and therefore the objective function is to maximize the value of 2x plus 3y. Next, let's look at the third component, constraints. We can check the resource limitations one by one. Let's start with the limitation for the number of lemons available. We see that there are 901 lemons available per day, and for each regular lemonade, Mary will use 4 lemons. Since Mary will produce x cups of regular lemonades, Mary will use 4x lemon to make regular lemonades. Similarly, Mary will produce y cup of strawberry lemonades, and each strawberry lemonade will require 3 lemons. Therefore, Mary will use 3y lemons to make strawberry lemonades. The total number of lemons used per day will be 4x plus 3y, and this total number of lemons should not exceed the 901 lemons available to Mary per day. So the constraint for the lemons will be 4x plus 3y less than or equal to 901. Next, let's take a look at the constraint for strawberries. There are 350 strawberries available daily. Each cup of strawberry lemonade requires 2 strawberries. Therefore, Mary will use 2 white strawberries per day, and this quantity should not be more than 350. The constraint for strawberries will be 2y less than or equal to 350. And we also see from the problem description that Mary wants to sell at least 50 strawberry lemonades. Therefore, there is a constraint such that y is greater than or equal to 50. Finally, we add the non-negativity constraint such that x should be non-negative, because it will not make sense to produce a negative number of lemonades. You can also add a constraint such that y is greater than or equal to 0. However, because the third constraint has already ensured that the value of y is non-negative, it is not necessary to include the non-negativity constraint for y in this problem. Now, with the linear programming formulations, we are ready to solve the problem. First, we draw the constraint lines. Next, we find a feasible region where all the constraints are satisfied simultaneously. Then, we draw a line to represent the objective function and move the objective function line to improve the value of the objective function until we reach the optimal solution. Next, we find the optimal solution by solving the intersection of the two constraints, 2y equal to 350 and 3x plus 3y equal to 901. First, we can simplify 2y equal to 350 by dividing both left-hand side and the right-hand side by 2. And we have y equal to 175. Then, we plug in y equal to 175 to the equation of 4x plus 3y equal to 901. Then we have 4x plus 3 times 175 equal to 901. Simplify the equation, we have 4x plus 525 equal to 901. Subtract 525 from both sides. We get 4x equal to 376.